IEEE Standard 80, specifically the 2013 edition titled IEEE Guide for Safety in AC Substation Grounding, addresses the topic of grounding. The standard indicates that there are no specific proximity requirements outlined between a delta lightning protection ground and a delta service ground. However, it provides some general guidelines. Firstly, the lightning protection ground should be installed as close as possible to the step voltage regulator or another source of ground fault current. Secondly, the service ground should be installed at the same point as the lightning protection ground or as close as possible. Thirdly, the two grounds should be connected together using a conductor that is at least the same size as the largest grounding conductor connected to either ground. Several additional considerations come into play when dealing with grounding systems. One consideration is the separation distance. In areas characterized by high lightning activity or in scenarios where there exists a risk of flashover between the two grounds, it might become necessary to increase the separation distance between them. Another point to consider involves ground rods. The quantity and length of ground rods employed for each ground ought to be ascertained based on the soil conditions prevalent at the site and the anticipated ground fault current. The conductor size is another aspect of importance. The conductor used to connect the two grounds needs to be appropriately sized to effectively handle the expected ground fault current. This ensures that the conductor can safely carry the current without overheating or causing other issues. The use of a grounding grid is another potential approach. In certain situations, it may be beneficial to use a grounding grid to connect the lightning protection ground and the service ground together. The specific size and configuration of this grounding grid will depend on the specific conditions of the site where it is being implemented. It's important to remember that when designing and installing grounding systems, it's always recommended to consult with a qualified electrical engineer. They possess the expertise to ensure that the system is safe, effective, and compliant with all applicable standards and regulations. Grounding systems are a critical aspect of electrical safety. They play a crucial role in protecting people and equipment from electrical hazards. A well-designed and properly installed grounding system provides a low-impedance path for fault currents to flow back to the source, which helps to quickly clear faults and prevent dangerous voltage build-up. A lightning protection system is designed to protect a structure from damage caused by lightning strikes. The system works by providing a path for the lightning current to flow safely to ground, bypassing the structure and preventing it from being damaged. A key component of a lightning protection system is the ground, which provides a low impedance path for the lightning current to dissipate into the earth. The ground should be properly designed and installed to ensure that it can effectively handle the large currents associated with lightning strikes. A service ground, also known as an equipment grounding conductor, is a safety feature in electrical systems that provides a low impedance path for fault currents to flow back to the source. This helps to quickly clear faults and prevent dangerous voltage build-up on equipment enclosures. The service ground is typically connected to the neutral conductor at the service entrance and then runs to all equipment enclosures throughout the electrical system. In the event of a fault, such as a short circuit, the service ground provides a path for the fault current to flow back to the source, tripping a circuit breaker or blowing a fuse and energizing the circuit. This helps to prevent electrical shock hazards and equipment damage. Step voltage refers to the difference in electrical potential between 2 points in the ground that are a step's length apart. During a ground fault, current flows through the earth, creating a voltage gradient. If a person is standing in the vicinity of the ground fault, their feet may be at different voltage potentials, resulting in a current flowing through their body. This can cause electrical shock. Step voltage is a safety concern in substations and other areas where high fault currents are possible. Ground fault current is a current that flows through the earth during a ground fault. A ground fault occurs when an energized conductor comes into contact with ground or a grounded object. The ground fault current flows back to the source through the earth, creating a voltage gradient. The magnitude of the ground fault current depends on the voltage of the system, the impedance of the fault, and the impedance of the grounding system. Ground fault current can be dangerous because it can cause electrical shock and equipment damage. The size of the grounding conductor is determined by the size of the largest ungrounded conductor in the circuit. The grounding conductor must be able to safely carry the ground fault current without overheating. Ground rods are used to provide a connection to earth for grounding systems. They are typically made of copper or copper-clad steel and are driven into the ground. The number and length of ground rods needed depends on the soil conditions and the expected ground fault current. Soil conditions play a significant role in the effectiveness of a grounding system. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for grounding systems because it allows fault currents to dissipate more easily. Soil resistivity varies depending on the type of soil, moisture content, and temperature. In areas with high soil resistivity, it may be necessary to use more ground rods or treat the soil to improve its conductivity. A flashover is an electrical breakdown of the air between two conductors, resulting in a sudden arc of current. Flashovers can occur due to high voltage contamination or damage to insulation. In the context of grounding systems, a flashover between the lightning protection ground and the service ground can be dangerous because it can create a path for lightning current to flow into the electrical system, causing damage. A grounding grid is a network of interconnected conductors buried in the earth that provides a low impedance path for fault currents. Grounding grids are commonly used in substations and other large electrical installations to provide a more effective grounding system. The size and configuration of the grounding grid depends on the specific site conditions and the expected ground fault current. IEEE Standard 80 provides detailed guidelines for the design and installation of grounding grids. An electrical engineer is a professional who is trained and licensed to design, install, and maintain electrical systems. Electrical engineers have a thorough understanding of electrical codes, standards, and safety practices. They can provide valuable expertise in the design and installation of grounding systems to ensure that they are safe, effective, and compliant with all applicable regulations. Electrical codes and standards are sets of rules and guidelines that govern the design, installation, and maintenance of electrical systems. These codes and standards are developed by organizations such as the National Electrical Code and IEEE. Compliance with the electrical codes and standards is essential to ensure the safety of electrical systems. Grounding systems are an essential component of electrical safety. They protect people and equipment from electrical hazards by providing a low impedance path for fault currents. Proper design, installation, and maintenance of grounding systems are crucial to ensure their effectiveness. Consulting with a qualified electrical engineer is always recommended when dealing with grounding systems. The information presented here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer for the design and installation of grounding systems. The grounding system is a critical component of any electrical system, providing a path for fault currents to flow safely to ground. A properly designed and installed grounding system protects people and equipment from electrical shock and damage. The National Electrical Code, or NEC, provides comprehensive requirements for grounding and bonding electrical systems. Article 250 of the NEC covers grounding and bonding requirements. This article provides detailed guidance on the types of grounding systems, the sizing of grounding conductors, and the installation of ground electrodes. The NEC also addresses the grounding of specific equipment such as transformers, generators, and motors. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents. Bonding helps to prevent voltage differences between metal parts which can cause electrical shock. The NEC requires that all metal parts of an electrical system, including equipment enclosures, raceways, and grounding conductors, be bonded together. Ground electrodes are used to provide a connection to earth for grounding systems. Common types of ground electrodes include ground rods, ground plates, and concrete encased electrodes. The NEC specifies the minimum size and number of ground electrodes that are required for different types of electrical systems. The resistance of the grounding system is a measure of how well the grounding system conducts electricity. A low resistance grounding system is desirable because it allows fault currents to dissipate more easily. The NEC specifies the maximum resistance of the grounding system that is permitted for different types of electrical systems. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the circuit if a ground fault is detected. The NEC requires the use of GFCIs in certain locations, such as bathrooms, kitchens, and outdoor areas. Surge protection devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, and other events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. The selection of appropriate grounding and bonding methods depends on several factors, including the type of electrical system, the size of the system, and the environmental conditions. Consulting with a qualified electrical engineer is always recommended to ensure that the grounding and bonding system is properly designed and installed. Regular inspection and testing of grounding systems are essential to ensure that they are functioning properly. Grounding systems should be inspected for corrosion, damage, and loose connections. The resistance of the grounding system should be tested periodically to ensure that it meets the requirements of the NEC. Any problems with the grounding system should be corrected promptly to prevent electrical hazards. Grounding and bonding are critical aspects of electrical safety. Proper design, installation, and maintenance of grounding and bonding systems are essential to protect people and equipment from electrical shock and damage. Always consult with a qualified electrical engineer for assistance with grounding and bonding. A delta system is a three-phase electrical system where the three phases are connected in a triangular configuration. In a delta system, there is no neutral conductor, so the voltage between each phase is the same. Delta systems are commonly used for industrial applications where a high voltage is needed. A Y system is a three-phase electrical system where the three phases are connected in a star configuration. In a Y system, there is a neutral conductor, so the voltage between each phase and the neutral is different. Y systems are commonly used for residential and commercial applications where a low voltage is needed. The choice between a delta system and a Y system depends on the specific application. Delta systems are typically used for high voltage, high power applications, while Y systems are typically used for low voltage, low power applications. The impedance of the grounding system is a measure of how much the grounding system resists the flow of current. A low impedance grounding system is desirable because it allows fault currents to dissipate more easily. The impedance of the grounding system is affected by several factors, including the size and type of grounding conductors, the number and length of ground electrodes, and the soil conditions. The voltage gradient is the change in voltage over a distance. During a ground fault, the voltage gradient can be very high near the fault location. This can create a hazard to people who are standing near the fault. Grounding systems are designed to reduce the voltage gradient and protect people from electrical shock. Touch potential is the voltage between a grounded object and a person's hand. During a ground fault, the touch potential can be very high. Grounding systems are designed to reduce the touch potential and protect people from electrical shock. Mesh size is the spacing between the conductors in a grounding grid. The mesh size affects the voltage gradient and the touch potential. Smaller mesh sizes result in lower voltage gradients and touch potentials.